Hello, and welcome to the AI Research Roundup. I am your host, Alex. Alright, today we're tackling a huge bottleneck in AI, the cost of training long context models. The paper is Training Long Context LLMs Efficiently via Chunkwise Optimization. So, the challenge with very long documents is that they require a massive amount of memory during training. This paper proposes a method called Sequential Chunkwise Optimization, or SeCO. It breaks long inputs into manageable chunks. Each chunk then builds its own map of calculations, or computational graph, and performs localized backpropagation, which is the process of learning from errors. This approach means the model only stores the memory-intensive forward activations for one chunk at a time, making training on long texts much more feasible. And it's great to see they also release the code for this work. So the GitHub repository has the full implementation for their sequential chunkwise optimization method and another one called SpaCO. It's got a quick start guide, installation instructions, and even code examples to get you running on either a single GPU or a multi-GPU setup using DeepSpeed, which is a popular library that helps manage training these massive models across multiple processors. So this figure really helps visualize how that sequential chunkwise optimization method works. On the left is the standard computational graph, basically a map of all the calculations. The green circles are the key value caches. A key value cache is a memory mechanism that stores context from previous chunks. You can see how they're all interconnected, creating a dense web that eats up memory. The right side shows the SeCO solution. It uses gradient checkpointing on the chunks, processing them one by one for the learning step, which is how it achieves that huge memory saving. Alright, and this chart really puts that efficiency into perspective. It compares different training methods based on their memory and time usage. In the bottom half, you see standard approaches like naive parallel training and 0-3, which is a popular technique for distributing model components. These are not very efficient. Then you have sequential chunkwise optimization, which we just discussed. It's much better on memory. But the real star here is in the top right, sparse chunkwise optimization, or SpaCO. This method builds on SeCO, but gets a massive speed up by only backpropagating through a random subset of chunks. So how can that sparse chunkwise optimization method just randomly sample chunks and still get good results? Well, this figure shows the key theoretical insight that makes it work. It maps out the flow of gradients, which are the signals the model uses to learn as they travel through the key value caches across different chunks and layers. The crucial part is what they call a gradient chain, which is the path a learning signal takes. The longest path is limited by the model's depth, or its number of layers. This property is what makes it mathematically sound to randomly sample chunks for backpropagation, enabling that massive speedup for sparse chunkwise optimization. And this figure gives us a great visual for how that sparse chunkwise optimization method actually sparsifies the process. On the left, you have the dense graph where all 6 chunks are interconnected, creating that complex web we talked about. But on the right, you see the sparse graph from sparse chunkwise optimization. It randomly keeps only 4 chunks for backpropagation, and crucially, it scales the learning signals on the remaining paths by a compensation factor, that k over t value. This ensures the result is an unbiased estimate, which means that on average, the learning signal is still accurate, preventing bias from the random sampling. And all that clever theory behind sparse chunkwise optimization, the random sampling and compensation, really pays off when you look at the performance benchmarks. These charts compare it against sequential chunkwise optimization and other methods. On the left, we're looking at training time, or what they call end-to-end latency. The red lines for sparse chunkwise optimization are much flatter than the blue lines for the sequential method, meaning it's significantly faster as sequences get longer. Then on the right, we see memory allocation, and again, both new methods are far more efficient than older techniques like 0-3 offload. When you put it all together, the performance gains are really impressive. The key takeaway from this work is that you don't need to process a whole long sequence at once. By breaking it down into chunks, and especially by using that clever random sampling with the sparse chunkwise optimization method, you can train these huge models much faster and with way less memory. This really opens up new possibilities for long context models. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.